Alright, so this video is going to discuss the directional derivative and how it connects graphically to what we've seen in the big theorem and the mega theorem. Okay, so I have a surface and I have different level sets drawn, and for our purposes right now, let's say we take a point A that is directly on one of the level curves, level surfaces, whatever language you want, or level sets, whatever language you want to use. Okay. All right. So then, in the last video, we did discuss the mega theorem, but for right now, let's just say that I have a directional derivative of a unit vector v of f at a, right? And let's say that that is 0. Okay. So what does this mean? Well, this just means that there's no elevation change in this context. Oops, elevation. Let's spell that correctly. Elevation change. Okay, so what that means for us is that, well, if I'm looking at the directional derivative with respect to v and there's no elevation change, right, that means I'm going, let me change colors here, that means I am progressing along the level curve. Okay, one of the two directions, I don't know which, but I'm going to call that v for our direction vector. Okay, and well, we know previously, right, that, well, by the big theorem, right, that this is precisely equal to the gradient of f at a dotted with v, and that's also 0. So then I can say that, okay, well, if I look at the gradient vector, that means by definition dot product that this should be perpendicular, right? So that when I look at that on a graph, the gradient vector should be perpendicular, and so it's going to be pointing across to the next level set at a right angle. Okay, and that would be the gradient of f. Maybe I'll do that in black just so you can see it more clearly. Okay, so that would be the gradient of f at a. Alright? And so what this is going to mean for us in the long run is that the gradient of f at a, and I should not include a vector there, so we'll just gradient of f at a is perpendicular to a tangent line to level curve at a. Right? So if I look at the tangent line at that point that points in the direction of the level curve, it's just going to be, the gradient vector is going to be perpendicular to it. And really the big takeaway here is just going to be that the gradient of f is going to be perpendicular to level sets. And consequently, if I just change my diagram a little teeny tiny bit now, if I think about steepest increase and decrease, okay, so let's say I have a point, oh, I don't know, let's do right there. Let's call that point A. Alright, we know that the gradient vector points in the direction of, or that it's perpendicular to level sets, right? So it's going to point up and at a right angle to each level set. And so actually the direction of steepest increase is in the direction of the gradient vector at a, okay? But what about decrease, right? So if I can keep going up and it's going to be perpendicular and it's going to go something like this, so I just need to make sure that at each level set I intersect it at a right angle. Well, decrease, wouldn't it make sense to define it the same exact way? So it's still going to be perpendicular to level sets, right? But now I think the vector is just opposite. Okay, so, and the steepest increase is going to be negative gradient at a. Okay, and again, as you adjust, this point A would need to adjust for each level set. Okay, so just an FYI on that. Okay, and that is actually all I have to say about level sets. Big takeaway, gradient vector perpendicular to level sets, and we're going to formalize it in a theorem coming up soon.